When you push a spacecraft out to the far edges of the solar system, the sun shrinks to little more than an unusually bright star. At that distance, traditional solar panels become completely useless dead weight. The standard fallback is nuclear power. But packing enough radioactive material to keep a spacecraft alive for a 20-year journey requires immense launch capacity, driving mission costs into the billions before it ever leaves the pad. That severe power restriction is a major hurdle if you want to study Triton, the massive, geologically active moon orbiting Neptune. Making things even harder, Triton is a navigational oddity. It sits in a retrograde orbit, meaning it travels in the exact opposite direction of Neptune's rotation. To chase down a moon moving backward, a traditional spacecraft would have to fire its thrusters to kill its forward momentum, reverse direction, and match the orbit. That maneuver alone demands thousands of pounds of chemical propellant. We can eliminate all that heavy fuel and expensive nuclear payload by rethinking how the ship moves. Instead of carrying its energy, the spacecraft can harvest it directly from the environment by operating as a magnetic glider. To execute this, the mission relies entirely on Neptune's unique environment. Coming in hot from Earth, the spacecraft drops a long, conductive wire. As the ship's high-speed velocity drags that wire across the planet's magnetic field lines, it generates raw electrical current. But Neptune has a highly irregular interior. As this diagram shows, its magnetic field doesn't originate at the physical core of the planet. It is severely offset by about 13,500 kilometers. Furthermore, that offset field is tilted 47 degrees away from the planet's actual axis of rotation. As Neptune spins, this misalignment causes the magnetic field lines to violently wobble around the spacecraft's orbital path. Because the ship is constantly moving in and out of the strongest magnetic zones, power generation doesn't flow in a steady, reliable stream. It hits the ship in massive surges, followed by deep electrical dips. To survive the uneven current, engineers have to equip the glider with specialized heavy-duty battery banks capable of absorbing sudden electrical spikes and smoothing them out for the ship's systems. Comparing planetary magnetic fields, Neptune's baseline is 27 times weaker than Jupiter's massive peak. To compensate, the glider casts a wider net. Instead of a 5-kilometer tether, it deploys a wire stretching 50 kilometers long. Pulling a 50-kilometer ribbon through space creates incredible structural tension, but Neptune's relatively low gravity keeps the physical stress on the material manageable. Once the tether is out and generating power, the ship uses a technique called asymmetrical drag to begin its hunt for Triton. By carefully adjusting the current flowing through that 50-kilometer wire, the ship physically pushes against the planet's magnetic field, slowly tilting its orbital plane to match Triton's backward trajectory. At the same time, the drag on the tether bleeds off the spacecraft's inbound velocity until it slows down exactly enough for Triton's gravity to capture it. Through a single mechanism, the glider utilizes an erratic, off-center magnetic field to steer and brake into one of the most difficult orbital paths in the solar system without burning a drop of chemical fuel. We can see the sheer engineering value of this design when we compare it to how a similar tether operates around Jupiter. Jupiter offers immense electrical harvesting potential, but its intense radiation belts limit tether length to just a few kilometers and constantly bombard the ship, threatening to fry internal electronics within a few years. Neptune is a much quieter environment. With lower radiation levels, a thin tether and sensitive onboard computers can operate cleanly for decades. Because the hardware lasts, the tether can stay deployed indefinitely, using slight magnetic adjustments to hold the ship in a perfectly stable orbit around Triton. By solving the geometry of Neptune's chaotic magnetic field, the electrodynamic glider proves to be a highly mass-efficient method for reaching and studying the furthest corners of our solar system. And with the field constantly wobbling around the ship, future engineers might even deploy dual tethers pitched at alternating angles, ensuring the glider never misses a single pulse of power.